So let's go ahead and do our first example. Let's do this guy. So we have an advanced spatial disoriented trainer allows the cab to rotate around multiple axes as well as extend inwards and outwards. It can be used to simulate driving, fixed-wing aircraft flying, and helo maneuvering. In one training scenario, the trainer rotates and translates in a horizontal plane where the location of the pilot is defined by the relationships as given. So you are given a relationship for position, r and theta in the transverse. R, theta, and t are expressed in feet, radians, and seconds. Knowing that the pilot has a weight of 175 pounds, we need to find the magnitude of the resulting force acting on the pilot at t equals 5 seconds. So, first of all, if we're looking at this problem, what type of motion is this? What type of motion? Curvilinear, okay. What directions is motion taking place in?
Radial and transverse.
Radial and transverse. So the trainer can go in and out in the radial direction, which is in the direction of your unit vector ER. It can also spin around. So that's in the direction of E theta, or in the transverse direction. It says that it is in the horizontal plane. What does that mean?
Z is constant.
Well, Z is constant,
Well,
yeah,
Z
but
is-
if I'm looking at the horizontal plane of motion, it's two dimensions, I'm not really calculating Z in that plane. If I calculate Z, I'm gonna have to turn the view over, and we'll look at that when we look at the free body diagram. Okay, are there forces involved? Okay, so we've learned chapter 13, which is kinematics, 14, which is kinetics. What are you thinking to yourself to solve this problem? F equals ma, for sure. If there's forces involved, you want to use the equations of motion for forces. What else do we might want to do? What are we trying to find?
The magnitude of force.
We want to find the magnitude of the force. So that means that, what is the magnitude? How do I find the magnitude? So the magnitude of any vector is going to be the square root of its components. The components in this case would be the forces in the radial, plus the forces in the transverse, plus, what other one do you have to include? Even though you're looking at the motion in the horizontal plane, it does give you a weight. If it's asking for a resultant weight, what do you have to include?
That'd be like the z-axis.
The z-axis. So we have to do the force in the z, okay? So that's what we're ultimately looking for. But to find the F's, what is my Newton-Euler equation? Very good. Let's try to speak up a little bit. Okay, very good. So how am I going to calculate A given R and theta? Yeah, you're going to first start with, let's write down our Newtons and we can pull this up. So we are given an R and a theta. So we have that R equals 10 plus 2 cosine pi divided by 3 times time. And we are also given a function for theta. So theta equals 0.1 times 2t squared minus t. Before we turn this off, we are also given a weight of 175 pounds, and we want to evaluate everything at a time of 5 seconds. Anything else I need to write down? I don't think so. Okay, so so first of all, let's go ahead, and someone said we had to take the derivatives. So if we take the first derivative of r, what are we going to get?
Angular velocity.
Oh, is it angular or is it linear?
Linear.
It's linear, okay? So what's the derivative of 10?
0.
What's the derivative of 2 cosine pi 3 over t? Very good. And what is the second derivative of r, or the first derivative of r dot? Negative 2 pi divided by 10, the pi is squared, this 2 is squared. All right, cosine pi 3t. Okay, now these, we all have to evaluate this, because let's go back to here. This is going to be an AR or an A theta, depending on, or an AZ, depending on the orientation. And we'll draw a free body diagram and find out that orientation. But for now, we do know that we have to evaluate each function of t equals 5 seconds. So if you get your calculator out for me, what is R evaluated at t equals 5 seconds? See if you all get 11 feet. And then, so one person calculate the first one person calculate the second. Who wants to calculate the first? Can someone calculate the first? Okay, and how about the second? Okay, and how about the third? Yes, please. Okay. And can you confirm that you get the following? Careful that you have your calculator in radians and not degrees. First one?
I verified the third one. Third one's right.
Okay, awesome. How about the first? Good. And how about the second? Who did the second one?
We got
Yep.
1.81377.
Perfect. Okay, great. So let's go ahead and move on. We have theta. We need to do the same thing. Why am I, let's take a step back. Why, if it isn't obvious, because say you don't have your toolbox in front of you, why are we going to, where's my purple? Here it is. Why are we doing this? Why are we taking derivatives? Yeah, so what is, if we are working in polar, what is AR? Can you tell me what AR is in your toolbox? It's like R double dot
Minus r omega squared.
minus R omega squared. What's A theta? Acceleration in the transverse.
R times
So R alpha,
plus
R.
2 R dot.
like this. And then what is AZ? Just AZ, yeah? Okay, so this is why we're going through all of the dots. So, or all the time derivatives. So this is also equal to omega, and this is also equal to alpha. So what do we have if we take the derivative of theta? We take the derivative of theta. Do you know what the derivative is here? Very good. And then what about this derivative? 0.4, very good. And we also have to evaluate this at 5 seconds. So what is this one going to be at 5 seconds? Can someone verify the following? And this was just 0.4. And this is in radians per second. Squared. Okay, so who can verify the top? Okay, very good. Who can verify the bottom? Yes? And the last one? Very good. Okay, cool. So we have all of our derivations, and we remember what you're looking for. So when you're solving these types of problems, to get to your answer, you kind of got to do a lot of things before. So make sure you're bookkeeping and that you can backtrack. Now that you have these derivatives, we need to look at the forces. I can't calculate the forces really without a free body diagram, without what I'm looking at, right? So if you have, it says if you're looking at the horizontal plane, and you have your spatial disorienter, so you had this picture, and this person was here, and you had this thing, yeah? And I'm looking at the horizontal plane, this was theta, and this was r. How are you going to, what is your free body diagram going to be? So, this is almost like Z looking at it. So, how would you how would you draw your free body diagram if I wanted to look at the plane ER and E theta, the radial transverse? My person, I'm gonna be looking down on my person, so, okay, don't laugh at my drawing, but that's the head, the shoulders, and the guy's feet. Okay, so, I told you, don't laugh. All right, so what type of forces are we gonna be looking at here? If I can extend and I can go around, I am going to have a force in both. I'm gonna have an FR and an F theta, yeah? Okay, so that's one plane. How would I draw my, the weight? Like if I flip this over to get the Z-axis, how would I draw my guy? So I would want ER, my vector ER on this side to go here, and I would want Z to go up. So then my little guy, now I'm looking at like this. So I still have my force in the radial, but now I have my force in the Z. What is force in the Z equal to?
Wait.
Just weight, because, so if I set up Newton-Euler's equation, F equals ma, is he accelerating? Does he have hydraulics? No. So it's just, so if this would be ma, my force in the z direction is just Fz, this would be the sum, equals m0. So F in the z equals weight, which was, how much did this person weigh?
175.
All right, so I already got one of my unknowns up here. So this is gonna be 175 pounds. So now I have to look at my Newton-Euler's equation for the direction of radial and transverse. So let's go ahead and do radial first. If I do the sum of the forces in the radial equals MAR. You told me earlier that AR is equal to R double dot minus R omega squared. Okay, how do I get mass from this? Mass equals weight divided by gravity, and in this instance, we're gonna use gravity as the 32.2. What do I get for mass? If you take 175 and divide it by 32.2, what do you get for mass? Say that again louder.
5.43.
Thank you. 5.435, what's the units?
Slug.
Slugs, very good. Okay, so that's mass. What did I get for R double dot? Good. So you have to be able to go back and find out what you calculated previously. Minus, what did I get for R?
11.
And omega? 1.9, good. What is the sum of the forces in the radial direction? If I'm looking at my free body diagram and the horizontal plane, that's here, this is the horizontal, this is the vertical plane. If I look in the horizontal plane, what are the sum of the forces acting in the radial direction? What's that?
ER times mass.
Just ER times mass. So ER is going to be the unit vector, but here I'm looking for F, forces. So I'm going to look in this direction, that's correct. But I want to look at the forces acting in that direction, which would be what?
Just FR.
Just FR, yep. So someone go ahead and calculate this row and confirm that you get negative 221.8 pounds. Can someone confirm that?
Yeah.
Awesome. 221.8 pounds. That is a negative, but you're going to square it, so it's going to be positive. Okay, so we have one more. Let's go ahead and do in the transverse. So if I do the sum of the, can you see this? Oh, that's light. That is light. That's okay. How about the sum of the forces in the transverse direction is going to equal the mass times the acceleration in the transverse. So if I'm looking at this, I'm looking now only in the direction of the transverse. So I'm only looking in this direction. What are the sum of the forces that occur in this direction? What is it? F in the transverse equals M. What was A in the transverse?
R alpha plus 2 R dot omega.
R
R dot
dot, thank you.
omega.
Omega, okay. So let's go ahead and calculate this. What do we, our mass was 5.435 slugs. What do we have for R? 11 times, what do we have for alpha? 0.4, good, okay. And then we have R dot. What do we have for R dot? Good. And what do we have for omega?
1.9.
1.9, awesome. Okay, if you calculate that, you should get 61.30 pounds. Could someone please confirm that for me?
Yes.
Awesome. Yes, I heard it. Yes? Okay, good, thanks. Okay, so now we have all of our unknowns. The question going back to what we were supposed to find was the resultant force. Can someone go ahead and say, what is 221.8 squared plus 61.3 squared plus 175 squared? All of that, I need the square root of. And I should get a force of what? A magnitude of what?
289.
That's what I got. Awesome. Questions on this? Yes?
Why did we divide 175 by 32.2 for the,
So 175, how much do you weigh?
that?
You weigh 175 pounds, okay. Is that your weight or your mass? When you stand on the,
That's my weight.
That's my weight,
Yeah.
okay. So our equations
Oh, you
are
have to
asking for
divide-
mass.
You have to divide by gravity.
Very good. So to get mass, we divide by gravity, very good. Any other questions? If I didn't walk you through this, would it have been difficult to find out where to start and where to go?
Yes.
A little bit.
Okay, so why don't we put the question back up and dissect it a little bit more, and then try almost the same thing with a different diagram, okay? So let's pick out keywords. The first one. The first, I broke these up into paragraphs. Technically, you don't need the first one, but it does give you a little bit of a hint. What does spatial mean? 3 dimensions. That right there means that I have to have 3 forces. That's your first indication, okay? Your second is that it can rotate inwards and outwards. In rectangular coordinate systems, can you rotate inward and outward?
No.
You can, you just have to break it up into components, right? So it's hard. In normal and tangential, do you have an inward and outward? Do you have those types of variables? No. Okay, that's going to be your second clue. Let's look at the next one. Okay, horizontal plane. Our motion is occurring in a horizontal plane. This is going to tell you that if it's rotating inward and outward and it's in a horizontal plane, that means you're working in the actual motion, the variable is going to be 2 dimensions. So just knowing that, what coordinate system do you think you're going to work in?
Polar.
Polar. Then it becomes really obvious down here when you have an r and a theta. When you are given an r and a theta straight out, always look towards polar coordinates. That's going to be your easy. I'm not saying you can't do another coordinate system. I'm just saying the easiest route is going to be polar. Okay? The next thing, you are given a weight. and you were asked to find force, that should be a key indicator that you are going to be using Newton-Euler. Now, you could use other types of equations of motion, but you've only learned so far Newton-Euler. Okay, later we're going to learn work and energy and impulse and momentum, and we'll decide which one of those three is best. But for right now, your force is just given, so use Newton-Euler, okay? So the first question, after you look through your hints and you write them down, first question you always ask yourself is what?
What type of motion?
What type of motion is this? So what type of motion is this? Particles can do two types of motion. What are those two?
Curvilinear and rectilinear.
Very good. And which one is this one?
Curvilinear.
Curvilinear. Very good. Okay. Your next one is going to say, is acceleration constant or variable? In this one, it doesn't really matter much. Okay, but it is going to be variable. Okay. But you are given r and theta, so you don't have to worry about a four-step process or straight line motion. And you just told me it was curvilinear, so straight line motion doesn't make much sense, right? Okay. So when you're looking at these types of problems, if you don't automatically think of a method, don't freak out. You just go back to asking mom, look for the hints, write them down. Write down what is given, what is known. Then to ask yourself, okay, what type of motion? Go through your questions. It will answer it for you. It will tell you what to do, okay? So I want you to take that advice and I want you to walk me through this one. Yes.
Just really quick before you erase the vertical plane, you have sum of forces equals m times 0, and then the line beneath it you just have equals to 175. Is it just because it gave us a weight, which is a force?
Yeah.
Okay.
Yeah, because, so I could have written it like this. 0 equals 175. So this just equals 175. Because this doesn't make much sense, right?
Right.
You just want to know what that value is.
Yeah. Okay.
Yeah. That's okay. You can ask questions. I guarantee the questions you are asking, the same people at home are thinking. So just stop me and ask. It's no big deal. The smooth bar rotates in a horizontal plane with a constant angular velocity of 60 RPM, radians per minute. If the radial velocity of the 1 kilogram collar A is v equals 10 meters per second, when the radial position is r equals 1, what is the velocity when its radial position is 2? So you tell me, what are some clues? Radial and transverse, why? So you automatically went to the coordinate system, polar, yeah? And in polar, we use unit vectors ER and E theta, which is radial and transverse. Why?
I was just gonna say, cycle of the slide.
You can't, well, I'm gonna delete the title. What is another reason?
Diagram.
Because you have omega VR.
Just because you're given angular velocity, could work in any other frame, that's okay.
But you also have VR moving. And you have r equals 1 meter, y equals 2 meters.
Could I not just use normal and tangential for a known
You
path?
can always use normal and tangential versus radial and transverse. Just one will usually be faster. You can always use the two. And you're more than welcome to unless the direction says yeah. What is the sleeve doing? Look at the motion. First, ask yourself, what type of motion is this? It's curvilinear. Okay, now ask yourself, is anything moving inward and outward of a circle?
Yes.
That should be your indicator that it's radial and transverse. Remember that your unit vectors indicate the direction of motion. If my sleeve is going radially, there has to be an ER. Or you have to break it up in components, right? It doesn't have to be, but we want ER would be the most efficient, correct? You are also, this is a pin, so even though you're not given a theta, this you can tell by the mechanical drawing that it can go around in a circle, right? That is your first indicator that this is polar. Okay? What else am I looking at? What other clues am I given?
60 RPM, W0.
What is the clue in this? It's constant. it is constant throughout the range that it is given, which means that alpha is what?
0.
Okay, that's your clue. This is a given, this is your clue. What other clues are given? There's a special word in here, what do I want to look at in the first sentence?
Smooth. No.
Horizontal, I'm not doing weight, okay? Not doing weight. So when I draw a free body diagram, what is my free body diagram gonna look like of this sleeve? What? What force is acting on it?
Radial and
There's gonna be a force that we call normal. Why is there a radial?
Because it's
Smooth. You can have a normal because there's gonna be a force between the sleeve and the bar, right?
Mhm.
But why would there be a radial force when it says it's smooth? No. What else am I gonna include in my free body diagram? Free body diagram includes kinematics and kinetics. What am I showing right now?
kinetics.
Right now I'm showing kinetics. Where's my kinematics? You said that this, oh, I'm writing in green again and you can't see green. Okay, so let's do, you have an m acceleration in the radial because my coordinate system is ER and E theta, correct? Okay, so this is gonna be what? Very good. Is there anything else that I'm missing in this free body diagram? It's given a mass. So what do I need to do? Nothing, I'm tricking you. Don't include a weight because it's horizontal plane. Okay? It's a horizontal plane. You're gonna use mass and maybe some equations, but it doesn't need to be in your free body diagram. Okay? All right, anything else? We're given something about V. It says that the velocity in the radial is 10 meters per second when R is equal to 1. I need to find a VR when the position is at 2. You are given, this is something you have to think through. So I want you to ask all your questions, okay? Because this could be a little bit tricky. So you are given these relationships. Yes?
Why are we putting force over the diagram? It's asking for force.
Okay, fair question. And we are gonna get there. We're gonna walk, so if you didn't do that, don't worry about it. Pretend we didn't have a clue because it gave us, I just looked at the diagram and I just drew a free body diagram of the picture I was given.
Yeah.
And the sleeve and the bar have some kind of contact. It said it was smooth, so I know that there's no force in the radial because it's a smooth bar, so it can slip. But I do know that it's gonna have a contact normal force, right? So I just drew it. Do I need to use it? I don't know. So if you wanted to wait to draw it, that's okay. You can wait. But normally we look at a picture and we just start putting everything we know down, right? So do I know if I'm gonna need alpha equals 0? No, but it was a hint, so I wrote it down. So I'm just writing everything I know down. And then the problem tends to lead you in the direction you need to go, okay? So that's why I'm just writing everything I know down. This is the most important. These are given to you, can you see this over the screen? No? That's okay, we'll rewrite. So we have a velocity in the radial of 10 meters per second when R is equal to 1. I'm looking for my velocity when R equals 2. When you are given initial conditions like this, what do you tend to think you have to do? What?
Force that.
4-step integrate,
Yeah.
okay? When you integrate, are the initial conditions usually your limits? Hey, that what? Yes? Okay, so I thought someone said no, I was like, wait a minute, yes we do. Okay, so that means that we have to integrate with a dv. If this is my limits, it has to be a dv paired to it, right? So this has to have a dv paired. What does this have to have paired?
DR.
A dr, very good. Okay, so if velocity is a function of position, is acceleration constant or a variable? Variable. What is it a function of?
Velocity.
Position, r, very good. So if I'm saying that velocity is 10 at r equals 1, that means velocity is dependent on r. A is going to be dependent on r. So what is my, if velocity is not a constant, I have to use my 4-step procedure, right? My first step is the kinematic relation. What is the kinematic relationship between A and V? Very good. But I said that I said that my acceleration is in terms of position. So what do I have to do? Very good. We have to multiply the top by dr and the bottom by dr to introduce that variable. What is dr dt?
R dot.
R dot or V. So I'm going to say V, and then I'm left with, so what I did, in case this part here is V. So I'm left with dV dr. Now I can go to step 2, which is what? Separation of variables. So, which is kind of that step 2, actually. This is kind of step 2. So I'm going to have dr over here, because acceleration is a function of position, so r has to tag along, v dv. Now, my question to you is, would you have done the kinematic relationship between v and r instead? Why would you, or would you automatically go to this kinematic relation? Yeah? I mean, if I was looking at it, I would have been like, oh, v equals dr dt. No worries, that's great. And I know that velocity is in terms of dr and dr, but now you see I'm not getting anywhere, because what is this? It doesn't get me anywhere. So that's, yeah, I know, right? I was like, yes, no. So I actually did this first, because I was like, oh, I have a V and an R. Then I was like, oh, wait a minute, that doesn't get me anywhere, because I don't want my two limits to be dr. I want my two limits to be V dr, and that's why I went to acceleration. So on an exam, or when you're in your careers, just because you think it's one thing and you get it wrong doesn't mean anything, just erase it and go somewhere else. Okay, it's fine. There's more than one kinematic relation. So that's why it got me here. So now I can say, I can integrate, which is step 3. I can integrate my acceleration for dr, and we said my limits are from 1 to 2. And now I can integrate velocity, which we said was from 10 to, I have to find. So we have 10 to v. I'm looking for v, so I can keep that as a variable, no big deal. This side of the equation I am totally fine with. This side of the equation, I don't know a. Now how am I going to find a? By using, so, why would we say that? Because given, it's okay. So I don't have the relationship for that with all the knowns, but I do have a relationship with force that can find it, because this v, all these v's, these are all in the radial, that from what was given. So that means that this a is ar. Okay, so now we can go over here, and I can equate to make my vector equation a scalar relation. And I can say that the sum of the forces in the radial direction equals MAR. What is AR from your toolbox?
It's R double dot minus R omega squared.
Thank you. Now, if I'm looking here, do I have any forces in my radial? No, so even if you didn't put this, it wouldn't even matter, because you're not even going to use the normal direction, okay? But it's a complete diagram, just in case you need to. So this is a 0. Okay, so now I can say R double dot, what is this really? This is the second derivative of position in terms of time, which is A. Okay, so since it's linear acceleration in radial and transverse components, I can only have one direction of linear, right? If we go back to the very basics, and we say that this is motion is ER, and this motion is E theta. If I tell you that the point P is moving, it has a linear acceleration, which direction out of those two unit vectors would you say is linear?
Radial direction.
ER, very good. So this is linear, which means it's your AR. That's what you're searching for. This is AR. You making that connection? Okay, so we're gonna solve this problem for AR. Divide by M, it goes away. Take this over to the other side. So I have AR equals R omega squared. For the interval 1 to 2, omega was given as a constant of 60 RPM. I do have to convert that though, because that is not in the correct units that I want. How do I convert that? Oh, very good. So we're gonna have 2 pi radian divided by 60. And this is gonna give you 6.28 radians per second. So if I go over here, I'm going to have, what's that squared, class? I have no idea. Or we can just leave it as
3,600.
like that, okay? So now we have this, and we have R as our variable. We're integrating in terms of R, so that's good. Keep it.
Wait, that's not right. You squared 60, you're supposed to square 6.28.
That's 39.43.
Okay, no problem. What is it, 39?
39.4.
39.4. No. That's a big difference. Are we sure on this one? Okay, cool. So here, we're just going to put in 1 to 2 of 39.4 R dr equals 10 V dV. All right, so if I integrate this, what am I going to get? So what is the integral of this? Yeah, so it's 39.4 divided by 2. And then the integral of V. Very good. To V. Okay, so if I plug that in and I solve for V, I should get, let me write the answer up here so we can all see it. I should get a velocity of 14.8, and I believe what units did they have us soon? Meters per second? Questions? So I think the hardest part on this one is making sure that you understand the hints that go on. The hints are going to get you through where to go. Yes, sir.
I think I got a little bit lost on the R double dot going to AR versus AR equals R.
This part right here?
Yeah.
No problem. Okay, does everyone understand this diagram here? Okay, can someone put this in words for me of exactly what I'm looking at? I'm looking at the polar coordinate. I am saying that P can be located by R, ER. That means that motion is occurring in the ER plane, okay? And we also know that it can rotate, right?
Yeah.
Okay, is the rotation, do you describe rotation using R or theta?
Theta.
Okay, so you're telling me that any motion linear, this is angular, is going to be R and theta. right?
Yeah.
Okay. If I was to describe the velocity and polar of point P, if I wanted to tell you the linear velocity, what parameter would I use?
The linear velocity would be r. Oh, d.
What is linear acceleration? Since these are time, and v is the derivative of r, and a is the derivative of v, I could also write this as r dot and r double dot. What is the angular velocity? What variable do we use? And x for acceleration?
Alpha.
This is equivalent to theta dot because it's a time derivative, and this is equivalent to theta double dot because it's a time derivative, correct? Okay. So when I look at r double dot, it means acceleration, linear acceleration. I'm telling you that the only linear that can occur is in this direction. Because if this guy moves in the transverse direction, it happens as a rotation.
Yeah.
But if it moves in this direction, it happens as a linear. So it can only accelerate linearly, meaning that r double dot has to be AR. If it was accelerating this way, then this symbol would be a theta double dot.
So I understand that much.
Wait, everybody else understand that?
Yeah.
Okay, so theta double dot, so when I ask you to write these equations and then we explain each term, and you say this is linear acceleration, you should know that that is linear acceleration in the radial direction. If you saw a theta dot, double dot, that would be angular acceleration in the transverse.
So why does AR equal itself minus R omega squared? Because AR
Yes,
is...
it's okay, yeah. It's saying that acceleration in that direction, and we can derive that after class together,
Yeah.
okay?
I guess I'm a little confused how something can equal itself minus a
You
non-zero.
were gonna have to take the derivative using the dot product, and we can do that together after class.
Okay.
Okay, so other than that, are we good? Yeah? Okay. And you can also understand that the acceleration in one direction is dependent on multiple variables, including itself in that direction.
Yeah.
So that might also make sense to you. Yes?
So force is 0 here and we just didn't consider the weight or the.
Why didn't I consider the weight?
Horizontal plane.
Horizontal plane. If this was in the vertical plane, I would have this, and I would have, this would be directed in. So this would be AR, and this would be AZ. Okay, so you have to pick out those cues. Questions on that? Okay, what's super interesting with this type of coordinate system is that you get to use it with orbital mechanics. In orbital mechanics, you can use the polar coordinates, like I said, and that means that you can also use your relationships for the Newton-Euler equation, correct?
Correct.
The only thing that's going to change is your force. In chapter 12, you were introduced to Newton's gravitational law, right? And it described the forces between two objects. It's the only thing that's going to change. So you're still going to use the F equals MAR and F equals MA theta. Your F is going to be the gravitational law, okay? So there is one thing that you do have to, now you have to calculate, because orbits, they can happen in different shapes, right? It could be a perfect circle. It could be an eclipse. How do you know, do you guys know how you would, like what would tell you if it's a perfect circle or what type of an ellipse it is?
If it's a specified major and minor axis.
Okay, what about something else? I think it's eccentricity. Have you heard of that?
Yeah, eccentricity.
Okay, so it's kind of like mechanical advantage and mechanical disadvantage. It's a ratio of terms. You guys know what mechanical advantage is?
Yeah.
Okay, so you talked about like the amount of force you have to put in for the amount of force you have to put out. So mechanical advantage would be like if I use a really long shovel to pick up a really heavy rock, the amount of force I'm putting in is super light compared to the amount of force the shovel is pushing on a huge rock.
Or it's like using a wrench too.
Yep, that's a good example as well. So it's kind of like that, and this one, it uses a ratio of here. So if, your book uses two different symbols, so we'll just say E for now. So if E is equal, the ratio of position times velocity squared over gravitation of the Earth's radius squared minus 1. If that ratio is 0, it's a perfect circle. This is in your toolbox. If you don't have it, I updated it so you can re-download it. So this is important, and it's important because your questions are going to look something like this. So if the moon is approximately 383,000 km from the Earth, assume that the moon's orbit around the Earth is circular. Right there, what is that telling you?
Eccentricity is 0.
Very good, it's 0. So you already have a given right there. And it wants to know the magnitude of the moon's velocity. How would you go about this? So if you, let's just go back to this guy. Let's just write down the equation. So we are given that E equals RV squared over G RE squared minus 1. And it is telling me in the problem that it's a perfect circle. And circle states that E is 0, right? Okay, let's go back to our problem and see what else we know. Okay, so we know the distance between the two is going to be and we also know that the radial, actually this is, we need to put this in just meters, right? Before we calculate. Careful of your units here. So this we don't want kilometers, we want it in just meters. So I'm going to say that this is 3.83 times 10 to the 8 meters. What is the radius of Earth? If you don't have that memorized, I think I also gave you that in your toolbox. But
It's like 61.
it is in kilometers, but we want it in meters, so just move that decimal place over. Okay, and we are trying to find this guy here. So we have everything, it's just a plug and chug at this point. What is the gravity that you're going to use?
9.8 and 21.
Yep, very good. So you have everything. You can plug and chug. So this is going to be velocity. You can also use, if you go to chapter 12, I believe you have a bunch of different formulas for like force. And I think I have, like here we go. So if you were asked to do a problem and you needed to use Newton-Euler's law, and you're going to do it in polar form because it's obviously making a circle, and that, say that satellite can move away from or closer to the moon, so you have your radial acceleration, but it can also orbit the moon or whatever it's orbiting. So you use your polar. But now you need to know the force. Well, I'm not going to tell you if the satellite is sitting on the Earth and it's going to have this force on it, okay? No, you have to use the gravitational force law, right? So this is going to be your force parameter, okay? And that's it. So that's your orbital mechanics. Questions on that? Yes?
Where do you find that equation of the?
I put it up and redid it, so when you reprint it, just print the one page.
Okay.
Okay, and it exactly looks like this. It has this equation, this table, and that figure. So just print the one page out and slip it into that, and you'll be okay.
Okay, so it's where it fits, but you can.
No, it will go after radial and transverse. Okay. But it's updated on Canvas. So that's orbital mechanics. I believe you have one problem with that. I want to do a challenge question now to bring you back. This isn't using gravitational force, but it is using radial and transverse. And does anyone have their book with them? So basically, you are going to resolve this one, but you are going to attach a spring to it. What is that? It's actually super easy. Hold on a second. We just did that entire problem. We just did this whole problem. I can't believe I got that reaction. What is the difference between, first of all, is there any difference? This is the exact same question, literally, with the same values and everything, except for you have a spring that's attached here. So it's pushing on this guy. Yeah, it's pushing on the sleeve. Is your four-step process going to change?
No.
Did acceleration change as a function of position? No, it's all the same thing. What is the one difference?
You have to have the spring force in the free body diagram.
That's it. That's it. Very good. So you had this diagram. You said that there's a force in the normal. A normal force, in the transverse. So we are working in radial and transverse. Now all you do is add the force of the spring, which is going to be Kr. Normally you see S, but it's R in this case because we're in radial. Okay? So you have R. That's it. So now when you do the sum of the forces in the radial equals MAR, it's no longer 0. Okay? It is now going to be Kr. And it's going to be negative, right? Because it's going against. Right? So it's going to be negative FR equals MR double dot minus.
R omega squared.
Thank you. Good job. Okay, so this is equal to KR. I'm going to move the M. And I'm going to, I want this by itself. So I'm also going to bring the R omega over, which equals R double dot. R double dot is the same as AR. You plug that into the four-step process, and you can integrate, and you're done. And this, what you're going to want to do is factor out the R. So you have R equals negative Km plus omega squared. So this is a constant. You can take that out of the integral and just integrate R. So you'll have negative K over M plus omega squared, the integral of R dr from 1 to 2 equals V dV from 10 to an unknown. That's it. Can you guys do that on your own from start to finish, knowing that the K is 20?
Most likely.
Could you, yeah?
Potentially.
Who has their book so I can I'm gonna erase this so you have to do it on your own, by yourself, no training wheels. You'll be okay, big boy, big girl pants on.